Morning, guys. So today we're going to begin talking about our last topic having to do with series, which is power series. The good news is if you're comfortable with convergence tests and the concepts of series, then power series shouldn't be altogether that scary. More good news. The only convergence test we're really going to use here is the ratio test. Bad news. It is more series work. Other bad news, it's more series work, and this time it involves an extra variable. So, you give and take. Basically, the idea here is that I split the series material up into two pieces so that no one piece is overwhelmingly terrifying. So let's just get into it here. Let me get the doc cam rolling. I'll show you what I mean. This stuff really isn't too bad. You just need to be brave. I promise. This, of course. Today is 11/4/2020. I hope everybody voted yesterday or sometime before. Interesting to see what happens with this election. It's the first time in my life that we've not known the result of the election the morning after, but we'll see. Today we're going to begin talking about power series. This is going to be section 11.8. This thing is not at all focused. Come on. All right, there we go. The important things for you to remember from previous sections in chapter 11.
Professor, is the document camera on? I can't see it.
Oh, it is, but if you guys can't see it, then let me see here. Oh, okay, here, let me try turning this. Yeah. Doc cam on. Screen share was not on. Thank you. Much better. All right. There we go. All right, now we can see everything. So it's important that we remember a few specific things. The ratio test, the estimation theorem, for alternating series, these are the main ones. What other big stuff do we use here? Well, primarily these. We will refer to the other convergence tests from time to time, but these are the main tools. Oh, I should also say, yeah, certainly geometric series. So every time where I kind of pulled a value out of a hat and I was like, oh, this series converges to the natural log of 2, or oh, this series converges to the square root of pi, or something silly like that, that information was actually coming from power series, right? So that was some a priori knowledge I had because I knew where we were going. A power series is an expression of the form I'm going to call it f of x. I'll use a capital F because it is a series, and we use capital letters usually to represent series. X because there is an extra variable in here, and that extra variable is going to be x. I'm sorry, n equals 0 to infinity. was just saying x as I wrote it. So f of x equals sigma n from 0 to infinity Cn x minus a to the n. Right. This is what a power series is. The first few terms of a series like this look like C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed, and so on. It's a series built up of power functions, or shifted power functions. Often you'll just see x to the n here instead of x minus a to the n. So, it would look like C0 plus C1x plus C2x squared plus C3x cubed. But you'll see them shifted like this as well. So remember, the x minus a is just a shift to the right by a units. So you really can think of these as just straight power functions with constants being added up. And if this were a finite expression, like if it were just these first four terms, we would call that a polynomial, right? That would be a polynomial. So these are really infinite polynomials. The sequence, the Cn, are called coefficients. And the number a is called the center. So power series is an expression of the form capital F of x equals sigma n from 0 to infinity Cn times x minus a to the n. And if you write that out in the long form rather than in the sigma notation, it looks like this. In other words, it's a big-ass polynomial. It's a polynomial that goes on and on and on forever. The numbers Cn, like C0, C1, C2, these things are called coefficients. And the number a is called the center. You've seen one of these before. You've actually seen a few of these before. I've snuck them into your homework in a few places. This thing, which you saw way back in the 11.2 homework a few weeks ago, this is a power series. If you write out the first few terms, this is 1 plus x squared plus x cubed. This is a power series. Cn is equal to 1 for all n, and the center, a, is 0. Another time you've seen an example of a power series. We looked at this one in preparation for exam 2. This is a power series. This is like x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This is also a power series. Where here, the CNs are 1 over n factorial. And again, a here is equal to 0. So oftentimes you'll see a being 0. Series which are centered at 0 are quite common, but not all the series we see will be centered at 0. Okay. Let me bring this up here. There are a few other little definitions I need to throw in before we can start working with these things. These series have a variable x in them. So the question, does this series converge or not, kind of depends now on what you're plugging in for the variable x. So the two definitions that are about to come up here have to do with the convergence of the series. Associated with every power series is a number capital R, which is greater than or equal to 0, can be equal to 0, called the radius of convergence. This is a number such that the series converges for all x values within distance r of the center. And then, so here's the picture. If you plot on a number line the center of your series, there will be some number r so this would be a plus r. You can walk left or right r units. So this would be a minus r. Such that if you take x's from anywhere in here, in this open interval, you're guaranteed the series converges. So one of the big things we like to do is try to find this number r. Right, so x values taken from anywhere in here will make the series converge. I'll work some examples for you in just a second. There's one other concept I have to introduce, though, and that's the interval of convergence. So associated with every power series is an interval of the form it's either a minus r to a plus r closed on both sides, a minus r to a plus r closed on the right, open on the left, a minus r, a plus r closed on the left, open on the right, or just straight up open on both sides, a minus r to a plus r, called the interval of convergence. This is the set, is the exact set of x values for which the series converges. All right, these are all of our preliminary definitions. So your series always converges when you plug in the center, because when you plug in the center, all the terms except the constant term are 0. So you've got a finite series. So you plug the center into your series, you always get something which converges. And then the question is, how far away from the center can you walk and still get a convergent series? Once you're done writing here, I'll be able to give you some examples. I'll give just a few more seconds. I know there's quite a lot here. Yeah. Okay. All right. So I'd like to return to this example. So we already said sigma n from 0 to infinity x to the n. We know what this guy's center is. Yes. Center a equals 0, all right, because x to the n is the same as x minus 0 to the n. And the coefficients Cn are all equal to 1. That's all well and good. This is also a geometric series. And the common ratio here is x. So the series converges if and only if the absolute value of x is less than 1, which is the same as saying -1 is less than x is less than 1. So here's your center. And here is your interval of convergence. If you take an x value from this interval from -1 to 1, you will get a convergent series. If you take an x value outside this interval, then you will get a divergent series. And the radius of convergence if you look at this distance right here, that's your radius of convergence, that's 1. So For a geometric series, very, very easy to get the interval and radius of convergence. You can just lean on the stuff that we've always known about geometric series. You set the common ratio absolute value less than 1. You solve the corresponding inequality, and that just lets you write down your IOC, your interval of convergence. Here we know that absolute value of x is less than 1 means the same thing as -1 is less than x is less than 1. If you don't remember how to unpack absolute value inequalities, this might be something you want to refresh. All right, if you've got the absolute value of some shit is less than a constant, that means you set the shit less than that constant and also bigger than the negative version of that constant. In this case, it's really simple. So that means my series will converge if and only if x comes from the interval, the open interval, -1 to 1. Since this is a geometric series, I get all the information right away. But with most other series, you'll get the radius of convergence, and then you'll still have to test what happens at the endpoints. I know that if I plug x equals 1 in here, I get a divergent series, because again, it's geometric. If I plug -1 in here, I get a divergent series because it's geometric. But power series in general are not quite that obvious. While we're looking at this problem, though, there's one other thing I want to do. Can we think of this series as a function? Well, it's a geometric series. And so as long as the absolute value of x is less than 1, as long as the series converges, it should converge to 1 over 1 minus x. It should converge to a starting value over 1 minus the common ratio. Why are you looking at me like you just did something bad, Bubba? Did you just eat the cat's breakfast? So if the common ratio, which here is x, has absolute value less than 1, then this series converges to this. Right? That's our formula for geometric series. They always converge to the starting term over 1 minus the common ratio. Well, this is a function of x. I can graph that function. It has a vertical asymptote at x equals 1. 1 over x minus 1 would look like this. So 1 over 1 minus x is the flipped over version of that. So it looks like this. I'm going to use some different colors here. I'll explain why in just a second. All right. So this whole thing here is the graph of 1 over 1 minus x. But the only part of it that's actually equal to that power series is the purple part. Oh, actually, I suppose I should, no, I should let this go all the way over to -1, shouldn't I? Yeah. Yeah, here we go. There we go. Okay. So the purple stuff here is the graph of f of x. Even though the blue is the graph, like the whole thing together is the graph of 1 over 1 minus x, this power series only converges to this function if the absolute value of x is less than 1. So that's from -1 to +1. Everywhere outside of that interval, this function still exists, but it's not equal to this series. because this series only converges if x is between -1 and 1. I'm going to show you some pictures a little later that kind of help you start to digest this idea, but I just wanted to introduce it here. So this series is geometric. It involves the variable x. We're able to figure out for what values of the variable x this geometric series does converge by setting the common ratio less than 1. And then we're able to use our formula for geometric series to say that this series is equal to this function as long as x is between -1 and 1. So I graphed this function. And I claim that this portion of the graph is the graph of this series, because this series is equal to this function. Let's do a couple more of these interval and radius of convergence calculations. Those are the first few things that we need to get comfy with. Before we revisit the x to the n over n factorial series, I'd like to look at one or two other things. So let's find the radius and interval of convergence for f of x equals sigma n from 1 to infinity -1 to the n plus 1 over n times x to the n. Let's try it. This, unfortunately, is not a geometric series. I cannot write this all as something to the n. First few terms of the series I can write out. This is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and so on. And here I need the ratio test. Most of the time when we're working with power series, we will be using the ratio test to find the radius and interval of convergence. This is kind of a standard problem. The ratio test, as always, says calculate L as the limit n to infinity, absolute value an plus 1 over an, which for this series is the limit as n goes to infinity, absolute value of, well, what is an plus 1? I take all this stuff and I swap the n's for n plus 1's. So that's -1 to the n plus 2 over n plus 1 times x to the n plus 1. I'm going to put that upstairs. And now I have to divide by an. That means I'll be multiplying by the reciprocal of an. That's n over -1 to the n plus 1 x to the n. And just like I would do in any other problem, I'm going to put the pieces together that are easy to work with together. So I'll write this as lim n to infinity, absolute value -1 to the n plus 2 over -1 to the n plus 1 times n over n plus 1 times x to the n plus 1 over x to the n. These pieces can be cleaned up quite a bit. -1 to the n plus 2 over -1 to the n plus 1 That's just -1. And then n over n plus 1 is what it is. X to the n plus 1 over x to the n is just x. And I can give everything their own absolute values, because everything here is being multiplied. The absolute value of -1 is just 1. So he goes away. I can pop out the absolute value of x, and I get absolute value of x, limit n to infinity, n over n plus 1 is positive, and this limit is 1. I just get the absolute value of x. Oh, isn't that neat? So the limit from the ratio test L is equal to the absolute value of x. Which means L will be less than 1 if and only if the absolute value of x is less than 1. Which is the same as saying, again, that -1 is less than x is less than 1. The center here was 0. We should probably say that. So now when I go to draw my picture for the radius and interval of convergence, we centered at 0, right? And I've just learned that this series will converge as long as x is between -1 and 1, just like the series we were playing with a second ago. So my radius of convergence is 1. The question is now, is my interval of convergence -1 to 1 open, -1 to 1 left closed, right open, -1 to 1 closed, or what's missing here? -1 to 1 left open, right closed. Which one of these is my interval of convergence? So I'm going to try to answer some questions here from chat. The inequality, like this guy going from here to here, the rule is if you have the absolute value, some shit is less than some constant, this always unpacks as the negative version of that constant is less than that shit is less than the positive version of that constant. And this is the key we need to unpacking the inequalities. This is stuff we were just getting to. I was curious about. Oh, okay. So then here, yeah, how do we know which one of these intervals is my interval of convergence? It could be any one of these, right? I know my radius, but I don't know what happens at the endpoints. There's only one way to figure it out. You take these endpoints one at a time and you plug them back into the original series. And you see whether you get something which is convergent or something which is divergent. Right, well, so here's the way to think of it. If you plug in 1 for x, that makes the ratio test inconclusive. Right, L here is the absolute value of x. So this inequality, this is what's needed to make L strictly less than 1. But remember, L equals 1 is inconclusive. That could go either way. So it's true that if x is either 1 or -1, this inequality is no longer satisfied. So we're no longer automatically guaranteed absolute convergence by the ratio test. But when L is equal to 1, the ratio test is inconclusive. So it could go either way. So what we really need to do is to plug -1 and +1 in for x here and see whether or not the resulting series converges. So in other words, it's not spoken for yet. It really could go either way. It really could be the case that any one of these is my proper integral of convergence. Is that clear? It's true that according to this inequality, x is not allowed to be 1 or -1, but this inequality isn't an if and only if the series converges. It's an if and only if L is strictly less than 1. Yeah, it's neat. All right, so the last thing we have to do on all these problems is check the endpoints. When x is equal to +1, if I plug +1 in, capital F of +1 is the sum n equals 1 to infinity, -1 to the n plus 1 over n times +1 to the n. And +1 to the n is just 1. So this is the sum from 1 to infinity, -1 to the n plus 1 over n. Does this series converge or diverge? Taking all bets. Is this a convergent series or a divergent series? Good, convergent. It's conditionally convergent, but it's convergent. The test I would use to show that that series converges is the alternating series test. And if we were being very, very careful, you would have to go through the alternating series test to verify that that series converges. Now, at this stage in the course, one of the reasons I like splitting the material up here is so that when you get to this part of these problems, as long as you tell me correctly whether or not the series converges and you're able to cite the test that would show it, I will give you credit. So I wouldn't require you to run the alternating series test on this thing. I would just require you to correctly deduce that the series converges and to cite the test that would do the job. When x is equal to -1, f of -1 here is sigma n from 1 to infinity, -1 to the n plus 1 over n times -1 to the n, which is sigma n from 1 to infinity, -1 to the 2n plus 1 over n. Does this series converge or diverge? First off, are you comfortable with the algebra? So here I'm multiplying like bases, -1 to the n plus 1 and -1 to the n. So I add the powers. N plus 1 plus n is 2n plus 1. So that's the algebra. And then the question is, does this converge or diverge? Any strong opinions here? If it were an alternating series, it would converge. But it's not an alternating series because 2n plus 1 is always odd. All right, the power of -1 here, 2n plus 1, that's always odd, which means this is always an odd power of -1, which is always -1. So this is actually negative sigma n from 1 to infinity 1 over n, which diverges as a p-series. Here p is equal to 1, which is not strictly bigger than 1. So my series converges when x is equal to +1 and diverges when x is equal to -1. Which means that +1 is in my interval of convergence, but -1 is not in my interval of convergence. So my interval of convergence is this fellow. Yeah, I'm not immediately aware of an obvious thing to compare against here, but the 2n plus 1 power always being odd means -1 to the 2n plus 1 is always -1. You can pop the -1 out, and what's left is sigma 1 over n. Sigma 1 over n is a divergent p-series. So this is a constant multiple of a divergent p-series. Therefore, this guy is divergent, which means -1 does not belong in my interval of convergence. So it has to be this guy. +1 does belong in the IOC because when you plug in +1, the series does converge. -1 does not belong in the IOC because when you plug in -1, the series does not converge. So the only option here is the interval that does not contain -1 but does contain +1. So this is my proper IOC. I've got two more things I want to do for you guys today. One of those things is more computation, so I want to get that out of the way. The other thing is very concept heavy, and I would like to spend more time on that than on the computation. So real quick, one more computation problem here. Find, I'm going to abbreviate them, ROC, radius of convergence, and IOC, interval of convergence, for the series f of x equals sigma n from 0 to infinity x to the n over n factorial. Hey, Bobos, okay. So again, here we would use the ratio test. L is the limit as n goes to infinity of an plus 1 over an, which is the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And I can rearrange. This is absolute value x to the n plus 1 over x to the n times n factorial over n plus 1 factorial. And the factorial factorials here, these are all positive, so I can lose the absolute values on them. X to the n plus 1 over x to the n, that's just x. So this is then n to infinity absolute value of x times, and then the factorials are n times minus 1 times n minus 2, all the way down to 3 times 2 times 1, and n plus 1 times n minus 2, n minus 1, n minus 2, all the way down to 3 times 2 times 1. So you can cancel. You can pop the absolute value of x out, and you get absolute value of x, then n to infinity, 1 over n plus 1. Which is the absolute value of x times 0. So L here is the absolute value of x times 0, which means L is less than 1 for all x. Right? No matter what you plug in for x, this thing is going to be 0. So here, the radius of convergence is infinity, and the interval of convergence is negative infinity to infinity. And here you don't have to test any endpoints because there aren't any endpoints. Right? The center of this series was 0, just like most of the other series that we played with today. The center here was 0. But when we calculate the limit L from the ratio test, we found that L is always 0. So L is always less than 1, no matter what you use for x. So this series always converges. This is actually a problem that we did back when we first learned about the ratio test. You guys may remember this was a homework problem, but now you can see it in the context of these power series. The other thing I want to do with you today is try to give you a feel for what it looks like when a power series is converging. And this is a little bit more complicated. I'm sorry, I've been reading about election stuff. It's been a rough night. Don't know about you guys. Did not get a lot of sleep last night. All right. Let's look at the first few partial sums. The first few partial sums of the series in question here. This is going to take a second, so I'll ask you to be patient. Four, yeah, okay. Okay, let's change all these colors. Oh, no, you come. You're all gonna be blue. Oh, and then some other color here I'm gonna e to the x. Let's put e to the x in something bold. Red, black. Red is all right. And let me unclutter this. So in red here, you have e to the x. You don't have to write anything. Just think along with me for a second. This will be our last few minutes of class today, and then I'll let you go. In red here, you have e to the x. All these things you just saw me typing, these are partial sums of the power series we were just looking at, x to the n over n factorial. If you write this out, this is 1 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial. That's what these terms look like, right? 1 over 0 factorial, x over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, x to the 4 over 4 factorial, and so on. So this is the S0 partial sum. This is the S1 partial sum. This is S2. This is S3. This is S4. This is S5. This is S6. Rather than being numbers, each one of these partial sums is now a polynomial. And the thing that they are going to converge to, rather than being a number, is a function, e to the x. So watch this. Here is the first partial sum. It matches our function, but only at the point which is the center. Remember, the center of this series is 0. So the constant partial sum, S0, matches with my function exactly, but only at that point, only at the center. S1, the first partial sum, matches with my function at the center and also has the right slope. You may recognize this as the tangent line. S2 not only matches with my function at the center and has the right slope, but it also has the correct curvature. This parabola, if you look very near the point 0, 1, looks an awful lot like that red function, doesn't it? The blue parabola not only has the correct, goes through the correct point with the correct slope, but also with the correct curvature. And as we go up and up and up in this chain, you're going to see the blue functions getting closer and closer and closer to the red function. Check this out. These are almost hard to distinguish. This is my third partial sum for this power series. And you see, if you stay close to 0, I can't even tell the red and the blue apart there. They look very similar. It goes through the correct point with the correct slope and the correct curvature and the correct third derivative. As I start marching out, using more and more terms in my partial sum, the blue graph looks more and more and more like the red graph. If we keep our focus, on the interval, say -1 to 1 here, I can't even tell the blue and red apart. And as I go further out and I use more and more terms in my partial sum, the blue and the red get even closer, even closer. This is what it looks like for a power series to converge to a function. And what you'll notice is that over here, on the right-hand side, this guy's staying very, very close to e to the x. On the left-hand side, he's not doing such a good job, right? The red function and the blue function diverge from one another. The blue function goes up here, the red function goes down here. But as long as you stay close to the center, the blue function and the red function stay very, very close to each other. And the more terms you use in this blue function, the better that approximation will get. So I could add the next term, which would be x to the 7 over 7 factorial. And you'll see that'll do an even better job than the previous guy. In particular, on the left here, he's doing a better job staying closer. All right, so this is what it looks like for a power series to converge to a function. You get this sequence of polynomial graphs, each one getting closer and closer and closer to the function that you are looking at, the power series that you're looking at. This is one example. There's at least one other example that I'd like to show you today. So let's do that. This is a fun one. Let me tune the colors here. Same sort of thing going on here. So we begin with the red function, which is sine x, and the first partial sum here, which is the tangent line. The next partial sum looks like this, and you see the blue getting closer and closer to the red. It's kind of like the blue is glued to the red at the center, and then you can sort of see the function conforming. So imagine you like pinned it down right there at the center, and then you can watch it like sticking from the center out. And as I get more and more terms of the series, my blue function is sticking better and better to this red function. I think you would have to agree. So the fun comes with saying, well, all right, how are you going to find all of these numbers? How are you going to find the series? All right, I give you the red function. How do you come up with the blue series? That's what we're going to be learning to do. Now, why do we care about this? Lots of reasons. Maybe the red function is really hard to integrate. This thing, as large as it is easy to integrate because it's a polynomial. So if I had to find the area under the red function from like 0 to pi, I could do that by finding the area under the blue function instead. Maybe the red function is hard to work with somehow. The blue function easier to work with. Integrals, limits, derivatives, all sorts of stuff where you can't work with the original function. Here, of course, the sine function is easy to work with, but there are some things like sine x over x that are hard to work with. So if you wanted to integrate sine x over x, you could maybe take this power series for sine x, divide everywhere by x, and integrate that instead. Those sort of tricks are really useful. In general, being able to write a complicated function as a sum of simpler functions is a big deal. That's something we get really excited every time we can do that. And most of us would agree, I think, that power functions, things like x, x squared, x cubed, those are relatively simple functions compared to things like sine x, cosine x, tangent x. Okay, so this is where we're going. All right, we're going to start finding these polynomials for a given function. And the place you start, once you're comfortable with the idea of what a power series is, which hopefully we're getting there, right? Don't worry about Bessel functions. We're not going to work with Bessel functions. But after you're comfortable with what a power series is and how to find the radius of convergence, the interval of convergence, all of that stuff, then the next big step is finding a power series for a given function. So the section that we're in right now is just, here's some series, find the interval of convergence, find the radius of convergence, all that good shit. The section we're going to be talking about right after this, and you do have a couple homework problems from 11.9 as well, is talking about the sort of shit that I've been showing you here today. Just in these last few minutes, right? It's talking about taking a function like 1 over 2 plus x and finding a power series for it. And we'll do that using what I call the geometric series trick. I'm not going to dump that on you yet today. So, and this whole stuff with differentiation and integration with power series, that's going to wait for next week. So the last little bits of stuff I'm going to do with you guys this week, I'm going to show you how to solve some of these more challenging questions. Back in section 11.8, there are some kind of tricky things there. Like this is cool, let P and Q be real numbers with P less than Q. Find a power series with specified intervals of convergence. That's fun. Can you find a power series whose interval of convergence is 0 to infinity? That's fun. Other fun stuff here. I definitely gave you some questions like this in your homework. So I tell you that a certain series converges, and I ask you, what can you tell me about these other related series? All of these things come from thinking about intervals of convergence and thinking about the shape that an interval of convergence can have. Let's do one more. We've got time, let's do it. How's about, those are all just more raw calculations, kind of boring. Let me look at some similar version of number 29 here. So I'll write this down. If sigma n from 0 to infinity, Cn, I'll say 5 to the n, is convergent, what can be said of sigma n from 0 to infinity, Cn negative 3 to the n, and sigma n. All right, so the blue down here is my version of that question. The trick here is to think of this series as a power series, but with something plugged in. So the trick consider this power series. In particular, note that the center is 0. So the interval of convergence is symmetric about 0. There is some radius of convergence. I don't know what that is, but I know I can walk left and right that amount and stay within the IOC. And what's more, I know that 5 is in the interval of convergence. All right, because sigma Cn 5 to the n converges. This is what you get when you plug x equals 5 in here. So I know that 5, x equals 5 is in the IOC. It could be that 5 is right up at the end point, or it could be that there's some distance between 5 and this end point. But I know the series is centered at 0, and I know that the series converges when you plug x equals 5 in, which means 5 has to be within the IOC. This means that r is at least equal to 5. Worst case scenario, r is equal to 5, exactly. But r is at least equal to 5, maybe bigger. Which means that -3 over here, definitely in the IOC. So this implies that x equals -3 is also in the IOC. So that first series, Cn -3 to the n, sigma n from 0 to infinity Cn -3 to the n, this must converge. On the other hand, Cn -5 to the n, he's harder to say. Well, that's f of -5. And -5 may or may not be in the interval of convergence. If r is strictly greater than 5, then yeah, 5 and -5 are both in there. But it's possible that r is exactly equal to 5. And if r is exactly equal to 5, then this is an endpoint. And there's no guarantee that the other endpoint is in there. So I'll end here with a question. Can we say whether or not x equals -5 is in the interval of convergence? I don't believe you can. I think there isn't enough information to say whether -5 is in the IOC or not, but we can say for sure that -3 is. And we can come up with some situations. We could describe different situations where -5 is in the IOC, and we could describe a situation where -5 is not in the IOC. And both of them are possible given what they've told us so far. So I don't want to overwhelm you guys. I'm not going to go any further than this. This is a good place to leave today, even though we've got a few minutes left. Begin by calculating intervals and radii of convergence. Right? I recommend reading section 11.8. It's a good section to read. They've got lots of good examples. Some of these concepts A little bit hard to wrap our heads around. Don't worry about the Bessel function stuff. I know this thing looks scary as all hell. Don't panic about it. All right, it's really not that scary. It's just a specific power series with lots of fancy notation. But read the other examples here where they're calculating intervals of convergence and radii of convergence, and they talk about the definitions and concepts behind power series. After you've done that, just try to get some practice calculating intervals and radii of convergence. That's what most of your homework is this week. Right? Most of your homework is problems like this. Find the IOC, find the ROC. 29, 30, these problems are also in your homework. They're challenging. They're fun. These deserve your time. You're going to have to think hard about them. They're not going to be obvious. And they're not going to be things you can get just by running a calculation. You're going to have to think hard about the concepts. After you've satisfied your curiosity there, read a little bit of 11.9. This is one of the last really hard sections that we're going to cover. So people do tend to have a difficult time with section 11.9. I'm just going to tell you now. The geometric series trick is not that bad, but it requires some getting used to. After we talk about that, we're going to talk about integration and differentiation of power series. People do tend to have a hard time with this. So spend some time calculating intervals and radii of convergence, and then read a little bit section 11.9. I'm not going to give you any of the calculus like integration and differentiation of power series this week. It's just going to be the basic geometric series stuff at the very start there. But then next week, we will be talking about integration and differentiation of power series. So I want you guys to kind of prepare yourselves. Good news, after that, we're going to talk about Taylor's formula. Taylor's formula is a complicated, scary looking formula, but it's not all that hard to use. And then you'll be done with series. No more series, yay. We're going to go back and talk about a bunch of other things. We're going to talk about surface area. We're going to talk about parametric curves. We're going to talk about polar coordinates. We're going to jump all over the place, but we will be done with series after 11.10. So knuckle down and get through these next few weeks. And after that, you will be free of series, at least until about halfway through differential equations. That is it from me. Any questions before we get going, guys? Okay, then stay safe. I hope everybody has a good day. Try not to be too distracted by the talking heads on the TV. Take care.